In this video, we're talking about molecular polarity. That is, whether or not a molecule is polar. We've seen before how a bond can be polar. We actually could classify it as either ionic, polar covalent, or nonpolar covalent, depending upon the difference in electronegativity of the two atoms in the bond. With a molecule, it's the same basic idea, except there's most of the time going to be more than one bond, and whether or not the molecule is polar or not depends upon all of the bonds in the molecule. Let's see. So let's just start out with some examples. Carbon dioxide, here's the Lewis structure, and from the Lewis structure, now this is important for doing this, we have to figure out what the shape is, the molecular geometry. 2 electron groups, 0 lone pairs, 2 bond pairs. This is a linear molecule, and that means that the real shape of this molecule is a straight line, just like it looks on the screen there. Now, each of these bonds we would predict to be polar because the electronegativity of oxygen is 3.5, that of carbon is 2.5, and so the difference in electronegativity is 1.0, making it a polar or polar covalent bond. So that means that the oxygen is pulling the electrons towards itself more strongly than the carbon this direction, but there's one over here doing exactly the same thing with exactly the same strength in the opposite direction. And just like a tug of war, if we have 2 teams that are exactly as strong as each other, pulling in opposite directions, that rope's not going to move anywhere. And so the electrons do not move anywhere. And so this is a non-polar molecule because the poles cancel. They're the same strength. Strength is the difference in electronegativity. The bigger the difference in electronegativity, the bigger the pull. Here, it's the same strength in exactly opposite directions. The poles cancel. Overall, this molecule is what we call non-polar, meaning there's no part of this molecule that's more negative or positive than any other. In this case, what we've done is we've replaced one of the oxygens in carbon dioxide with a sulfur. It's still a linear molecule, so it's straight. And this bond here is still polar. The difference in electronegativity between oxygen and carbon is 1.0, making it a polar bond. But the difference is on the opposite side, we have a different element which has a different electronegativity. It just happens to have about the same electronegativity as carbon. So this is a nonpolar bond. It cannot balance the pole here, so this is a polar molecule. And in this molecule, the electrons are going to be shifted over towards the oxygen and away from the sulfur. In this molecule here, sulfur dioxide, the central atom has 3 electron groups, 1 lone pair, 2 bond pairs. This is a bent geometry. And even though we have the same element on both sides, oxygens, the difference in electronegativity here is 1.0 on both sides. But because this is bent, remember, it's basically pointing down in these directions here. The poles do not cancel. They're not opposite each other. And so this molecule will be polar because the poles do not cancel. This molecule here is nonpolar. Okay, let's look at why. First of all, the electronegativity of fluorine is 4.0, carbon is 2.5. The difference in electronegativity is 1.5. So each of these bonds is a polar bond, a polar covalent bond. However, what's the shape of this molecule? Well, the central atom, carbon, has 4 electron groups, 4 bond pairs, 0 lone pairs. This is the tetrahedral geometry. And in the tetrahedral geometry, it's very symmetric. The poles, because these are all the same element, they all pull at the same strength, they all cancel each other. This is a non-polar molecule. On the other hand, if we replace, say, 2 of these fluorines with hydrogens, this will be a polar molecule because now the poles don't cancel. And to see that, I know that in the Lewis structure here, it kind of looks like they cancel, right? Because the hydrogens are opposite and fluorines are opposite, but that's not the real shape of the molecule. This is a tetrahedral geometry, and so if we look over here, it doesn't matter which 2 spots you put the fluorines and the hydrogens, they're not going to balance each other. See, this is 109 degrees here, right? So the pole here by the fluorine is not going to balance the pole here by this fluorine, and hydrogen, the carbon-hydrogen bond, the difference is 0.4. That's a non-polar bond. So the poles do not cancel. This is a polar molecule.